Okay, we're going to move into section 3.2, which is called perturbation methods. And the term perturbation, at least here in mathematics, as you can read here along with me, is when we are trying to solve a particular problem by comparing it to one that we already have a solution for. We kind of have done this a little bit with our accident and ambulance location, or accident and police car location methods. Of course, my cats are going to start to meow now because I just started to tape, so sorry for the glare on here. I'm having a little bit of a problem figuring out how to get the lighting just right in my living room, so the contrast isn't particularly great. But let me set up the situation that we're going to be dealing with here for the next few minutes. So we're going to take this area now, and now instead of having like a 1 mile of road or an S miles of road or an A miles of road, now we're going to have an actual geographical area. And what I've done is I've color coded it here. Unfortunately, the background is contrasting poorly with my red, but we are going to let x1 and y1, these are going to be random variables that are actually an accident location. So I'm going to underscore those there as random variables. In this particular accident location, I'm going to be solving problems for the next few slides in general, and then also for a specific situation. So if this is my general random variables, and this will be my specific location. So if I were looking at an XY plane here, the coordinates of this point, well, it turns out that this is going to be at the position of 2 miles. So I'm going to have my x-axis is going to be in miles, and it's going to have these positions of 2 miles, then a place called B called 3 miles. Then we'll also have right here, that's going to be at 4 miles, and then the total length of the x is going to be 5 miles. Now, one thing I did not do very well here is I did not stick with the way the book does it. So this actually, they don't stick with my normal convention of variables and values, but this actually is a capital X, X naught. But notice that I'm not underlining it. It just is the book's notation of saying that that's how long the x-axis is. Same thing up here with the y. The book actually uses a capital Y naught, and that's an actual numerical value. So I'm going to spend a few minutes here just getting you familiar with the situation and the notation. All right, so x naught and y naught are actual just numbers. Of course, my pen is running out right now as I'm using it. So our numerical values. Normally I would call them a little x and a little y, but I'm going to stick with the author's notation because there's some pretty complicated equations we're going to be doing. So x naught and y naught are numerical values. x1 and y1 are random variables for my accident location. And then I probably should score on here as well. So if y is 3 miles, then for my very specific example, this particular blue dot is going to occur at 2, 1, and then this red dot is actually going to occur at 4, and this ends up being roughly 1.5, so it's not really to scale exactly right, but it's 1.5. And then, by the way, the height of this barrier here is at 2. All right, so I'll talk about that here in just a second. Okay, now we've got x2 and y2 are my ambulance, ambulance location. So those are random variables. And then I have this d. So d is going to represent the rectilinear distance between my accident location and my ambulance location, and that will be, and we know from like the last lecture, that rectilinear distance is going to be the difference between the x coordinates plus the difference between the y coordinates. So I will write up here that d is the rectilinear distance, or Manhattan distance, however you want to say it, rectilinear distance between the accident and the ambulance, between the accident and I should probably be sticking with the colors here, ambulance. And of course that's going to be a random variable as well. Now we know from a previous lecture that what if I was just looking at D being the difference between two values? Remember when we had just 1 mile of road, or just S miles of road, we said that the distance between an accident and an ambulance, or an accident and a patrol car, would be the absolute difference here. And we already know that that's just 1/3 the length of the X. So if this was just a road of 5 miles, we know that the expected X distance would be 1/3 whatever the total length of the X was. So that would be 1/3 5. But we can do the same thing for Y here. That's just going to be 1/3 times the Y distance. So this is here the general form. It would be 1/3 times this value plus 1/3 times this value. And so for our particular problem, where do we get that 8/3 from? Well, we got that by 1/3, and then we had 5 plus the 3. So that's where that 8/3 comes from. So what we're doing is now we're going to put a barrier here, so we're complicating our problem a bit. Now we've got a barrier, and we're saying that it's negligibly thick. It's going to be at the point, and the authors call it B. So B is at 3 miles on the x-axis, and it's at a height of 2 miles on the y-axis. So I kind of want to, I'm not going to really be able to see this very well, but it's a good idea to do it this way, like that. Okay, so in a real situation, what might an actual barrier be? Well, it certainly could be, this is maybe the 51 freeway, and this is one side of it, and this is the other side of it. It could also be maybe a double yellow line that you're not supposed to cross, or it could be a wall or a bunch of buildings. So what we're doing is we're permutating our problem from the last time, where we were just looking at the distance between two random points on whatever a certain number of miles. Okay, so now I believe we have pretty much set up everything I wanted to say. Is there anything else I wanted to say about the problem? And I'm going to have to I'll keep drawing this just to kind of slow myself down as I go through these slides. So the question is now, what is the expected distance between the accident and the ambulance now? So this D right here, this is the rectilinear distance between them, and I actually should point out up here without the barrier, and then what we want to do is we want to figure out what would the distance be now that we have the barrier. So let me amend this. D is the rectilinear distance between accident and ambulance, and then I'm going to write without the barrier, because we're going to incur some extra distance now because of this barrier, and that's what the next set of slides are actually going to be working on. Okay, so now the next slide, I'm going to define a couple of different random variables for this problem, and I might have to come back to this maybe, so let me hold that out. So here's our area again, and thank you for your patience as I redraw some things, because I wish that I had caught this earlier. So that's a big X, that's a big Y. And then these coordinates here, maybe I should just write the coordinates down. Maybe that would just be a bit easier. So the coordinates of this blue point, which is actually where the accident is, that's going to be at 2, 1, and the coordinates of the red are at 4 and 1.5. The height of this barrier here, they call that A. That was on the previous slide. So the height here, A equals 2. So right here, the coordinates at the tip top of this barrier are going to be 3 and 2. And then this is obviously 3 and 0. So on the previous slide, we defined that the letter D, I'm skipping down here a bit, is the rectilinear distance between the points if we don't have a barrier. Now I'm going to define D prime to be, and I'll make that kind of a bigger prime there, be the distance between the points when we have the barrier in place. And I'm going to let D, so these are both random variables also, DE is going to be, with a subscript, is going to be the extra distance traveled that is due to the barrier. So we can say then that we can express these things in just a linear equation that, where do I want to put it here so you can see it? So we have D prime is going to be the regular distance that we would have had without the barrier plus the extra distance that we have with the barrier, okay? And then what we can do is we can go up here, or we can do it down here, I guess. We can say, okay, so the expected distance between the 2 points with the barrier in place, that's just going to be the expected distance without it plus the expected extra distance. So what we're doing here is we're kind of breaking this problem down into little pieces that we can chew. Now here's an interesting point. The extra distance is only going to be bigger than 0 when both of the points are on opposite sides and below the barrier. And I'm going to explore that in a little bit more detail here. I think on the next slide is when I actually do it. Do I? Hang on a second. Nope, I don't. So let's just do it here. This is fine. All right, we already know, just some things we already know, that the expected value of the rectilinear distance is this. I just pointed that out. Now, what do we mean by this yellow piece here? Let's look at my situation right here. Suppose I had, what if I had a point, let's just look at a couple of different scenarios. Now this I didn't rehearse for, let's see what happens here. So we know that blue is the accident and that red is the ambulance, right? And if I take a look at different coordinates for each one of these, and I wanted to look at, I'm just going to do a couple of different scenarios here. So suppose I took an accident and I put it over, let's say up here somewhere. So let's say I put it at 2 and, let's say, this is 3 miles high, right? So suppose I put it at 2 and 2.5, all right? So 2 and 2.5. So if I put it up here somewhere, and I'm just going to make a tiny little X here where that might be. But notice that it's above the barrier here, right? And suppose the ambulance was where it is now, like 4 on the X axis, but not at 1.5. Let's just make it at 4 and we'll make it 4 and 2.5 too. So that would be right about there. It's not a really good example, but all right. So the rectilinear distance between these 2 points, first of all, it's 0 in the y direction, and it's the absolute value of 2 minus 4 in the x direction, but there's no extra distance. In other words, for me to get from here to here or here to here, the distance, the barrier is not a problem at all. And in fact, what if I keep my accident here at 2, 1, I'm sorry, 2, 2.5, let's do that one again. And now I'm going to take, and let's just use the current point, right? What if my ambulance is at 4 and 1.5? So does the barrier matter then? No, it doesn't at all, because rectilinear means I can go any way I want. I could go down here and over here and then down, or I can go all the way over here and down. In other words, I can get from this little point right here to this accident right here without worrying about the barrier at all. It's no problem. And I could also have put this little dot down here and then the ambulance up here, and I'd have the same situation, that whenever I have one of the points that is above the barrier and one is below, or if they're both on the same side, certainly, we don't have any problems or any extra distance incurred because of the barrier. So we only have extra distance when both points are below the barrier, because watch, in order for me to get from the blue to the red or the red to the blue, I can't go through the barrier, so I'm going to have to go from 2 to 3, one here, and then from 2 to 3 here. So 1 plus 1 plus 1, which is 3, plus a half. So it's going to take me 3.5 miles to get from here to here. Whereas if I had no barrier, it wouldn't be 3.5 miles. It just would have been from 2 to 4, which is 2, plus 1 to 1.5. So it would have been just 2.5. So I'm only going to incur distance when I have my points like that. So that's an important thing to note. Now, if my expected distance, my extra distance, is because of the barrier, now what I'm going to do is break that up and use that law of total probability, although it kind of degrades into something easy to use. But if I just take a look at this component right here, this expected extra distance, the expected extra distance that I'm going to break that up, and I'm going to have the expected extra distance, given that, this seems really weird, but that the distance is equal to 0 times the probability that that extra distance is equal to 0. And that term's going to go to 0, but we also have extra distance, given that my extra distance is bigger than 0, times the probability that my extra distance is bigger than 0. So this seems kind of crazy because this whole term right here, that's going to be 0. If my extra distance is already equal to 0, then it doesn't matter what the probability is. So my expected extra distance is actually going to have to be this conditional probability term right here. All right, so let's move on to the next slide. I've got all kinds of paper out here. And now we get to see it a little bit better, I think. So let me get this out right there. Gosh, there's a lot of glare there, isn't there? No, that's all right. Okay. So this slide kind of just summarizes what I just did. So we said if this point is at, what did we say it was? It was at 2, 1. And this point here is at 4 and 1.5 here. And again, this is a big capital X and this is a Y. I know I'm going super slow, guys. I'm sorry. I just think it'll be helpful in the long run. So DE, when you look at what we just did, my extra distance is really going to be 2 times the vertical distance from this red point. So that's the point that's closest to this barrier tip here, right? Remember, this is at 3, 2. So the extra distance that I travel in going from these points ends up being 2 times this vertical distance from the red point to the tip of the barrier. So what is that extra distance? Well, that ends up being, it's 2, because there were 2 here. The distance here is 1/2, but it's twice, because I have to do it twice. If I go from the blue point to the red point, I go up here, and that's when I hit that first half piece right there. Then I go over, and then I have to do it again right here. That's the extra distance that I'm traveling. And so this is just an example, using my little bitty area here, of how a person would compute that. Now technically, because this is actually a numerical value, this probably shouldn't be a big D. It probably should be represented as a little d of e, because this is a random variable and that is an actual value. Now, what if there had been no barrier? We figured this out, right? So this is a random variable, but using my example here, it would be a little d here. We said if there's no barrier, we did it on the last slide, no barrier, we go from 2 to 4, that's 2, and then we go from 1 to 1.5, so it would be 2 in the x direction plus 1/2 in the y direction, and so we would have 2.5 miles in this situation. And the distance between the points With the barrier, again, this probably should be a lowercase. What was it? We'd have to go from 2 to 3, or we could do it this way, it doesn't really matter. We can go 2 up to 3 here, so we would have 1 going this way. Then we have to go all the way over from 2 to 4, so then we'll have 2 going that way. And then we have 1/2 that we have to come down to get to the red dot. So with the barrier, this ends up being 3.5 miles. And as we predicted up here, the extra distance, again, we said that should be a lowercase d, ends up being, well, that would just be the d prime minus d. So we have 3.5 minus 2.5 equals 1 mile. So really what I'm doing down here is just showing you why this is true, okay? So now that we can, hopefully we can see that this all makes sense. Now I'm going to introduce some more random variables. Yippee yippee. Now we're going to call z1, that's going to be the vertical distance from my random blue, my accident, to the tip of the barrier. So that's going to be from x1, y1. So remember, this is the accident location. To the tip of the barrier. So for our case here, if I was just looking for the lowercase value of this, or the numerical value, and again, I didn't do a good job here. In this case, that would be going from 1 to 2, so that would just be 1 mile that way. And z2, that's going to be the vertical distance now between my ambulance location, which is x2, y2, and those are random variables. So remember, this is the accident location. I'm going to get into something here. Accident location. And if we were looking for a numerical manifestation of that from this problem, that would actually just be going from 1.5 up to 2. So that would be 1/2 mile. And I can represent my random variables here, if you like, by using the notation from the textbook. So the textbook calls the height of this barrier, they say that this 2 right here, that they say A equals 2 and B equals 3. So A and B are just the coordinates in a really weird way of where the barrier endpoints are. So Z1 then, we could represent Z1 as just the height, which is at A of 2 miles, minus the Y location of the accident. So we could actually represent Z1 then as this numerical value A, not a random variable, minus the random Y component of my accident. And for Z2, we can represent that as A minus, but now the Y component of my, I said accident here, didn't I? I meant to say ambulance. Darn it. I'm doing this later at night, and so this should say ambulance. So sorry. So this is the Y component of my ambulance location. And now for that, remember from the previous slide, what we're trying to figure out is, ultimately, where we're going here, is we're trying to figure out that the expected extra distance is going to be equal to the expected extra distance given that the extra distance is bigger than 0. And that is going to be the related to this equation right here. So my extra distance, given that it's bigger than 0, is going to be 2 times the minimum value of Z1 and Z2. And that's exactly what we did up here with just a real numerical problem. Now we're just extending it to terms of random variables. So the minimum of Z1 and Z2 happens to be that half mile because the red dot was closest to the barrier, and we're going to travel 2 times that distance as my extra distance. So this is going to be important right here when we move on to the next slide, which doesn't really say anything. I really just kind of summarize it on the next slide. Kind of have a lot of slides in here. So let's move over here. Oh, I know why I have this, because we spent some time in the last lecture, and I think I put it on an exam, your exam, somebody's exam, that the expected value of the minimum of 2 random numbers on 0s is s over 3. That's just the general representation. For our problem here, when we have x going up to 5 miles, y going up to 3 miles, that we know that the extra distance, given that the distance is bigger than 0, that's going to end up being 4/3 miles. Why? Because it will be, well, s over 3. We said that this is the same thing as saying that this is the expected value of 2 times, this is from the previous slide, minimum of Z1, Z2, which is just 2 times the minimum of Z1, the expected value, sorry, of the minimum of Z1 and Z2. Hang on 1 second here. So let me finish this brace up here. So we have 2 times the expected value of the minimum of 2 points that can be on this barrier here. So this barrier again goes from 0 up to a equals 2, which is almost the same thing as, remember what we did in a previous lecture. It'd be kind of like looking at a road that starts at 0 and goes to s equals 2 miles. Well, that road is just this barrier right here. So now we have 2. We know that the expected value of the minimum was 2. I'll just write it this way. It's 2. Now we have s over 3, but s in this case is 2. So we have 2/3 times 2 equals 4/3 miles. In this case, for this particular situation. So I wanted to point that out, but anyway, just kind of pointing this out. And so that is for our specific situation. Now what we can do is we can put most of this all together in the next 2 slides. And I know this is a little bit long, but I think we've just got, yeah, just 2 more slides to go for this lecture. So, okay, so now what we're going to do is, remember what our ultimate goal is. We're trying to figure out what is, let me write up here just because sometimes we forget where we're going, right? We're trying to figure out, this is our objective, is we're trying to figure out what is the expected value of the extra distance with the barrier. So this is distance with barrier. And we said that's the expected distance without the barrier plus the expected distance, the extra distance, and we just figured out what that was. But we could write it this way, given that DE is bigger than 0. Kind of get a little sloppy there. Okay, so now we have to figure out what the probability is of it as well, because we know that this term here has to be multiplied by the probability that the extra distance is bigger than 0. So that's the term that we're trying to work out here. So the probability that the extra distance is needed is as follows. We already said that the extra distance is only going to be required when we have a point in this area here and another point in this area here Or we could switch it, right? We could put the red point here and the blue point here. So we have to figure out what this probability is. So if the accident is in the region bounded by, again, 0, 0, so put the coordinates in here, 0, 0, this is 0, 2, this is 3, 2, and this is 3, 0 here. Accident there, and the ambulance is bounded by 3, 0, 3, 2, 5, 2, or 5, 0. That's one way we have extra distance incurred. But then we have this magical word or. Or we could have the red dot, the ambulance, bounded by 0, 0, 0, 2, 3, 2, and 3, 0. And then the accident over here with bounded by 3, 0, 3, 2, 5, 2, and 5, 0. So what I'm going to do is I'm going to express it for our particular problem on the left, and then we'll put it in general terms over here. So remember, the tippy tip of this barrier here has A equals 2 right there. I think we've got just about everything here. So now, the probability that my extra distance incurred here is bigger than 0 is going to be the probability of this situation, which I called lowercase I, and then II here. So how do we get this? Well, we're just going to use geometric probability here. My total area is going to be 5 times 3. So that's where this 5 times 3 comes in. So this very first term is going to be the probability that the accident is in this particular region bounded here. So what is the area of this region? Well, it is 3, 0 to 3, times 2, 0 to 2. So we have 3 times 2 over the total area, 5 times 3. And the ambulance, now we have to account for this area. So this is the probability that the accident, maybe I should write this down. This is the probability of the accident, accident is here, and I'm just going to circle this right here. I know this isn't very pretty. And then this one, this term here, is going to be the probability that the ambulance is here, which is right there. So where does that come from? Well, we have 5 minus 3, so that's the 2 miles here, 5 minus 3 times 2 over the total area. And now we switch it. Red dot here, blue dot there. So now this 3 times 2, 5 times 3, that is going to be the probability that the ambulance is now here. So this is probability. Ambulance is here. And this one will be corresponding to here, so that's the probability the accident is now on the other side of the barrier, the right side. So for our specific situation, this is how we would get these probabilities. It's just 2 times this term right here, and it works out to be 0.213. And I think I'm just going to carry this down so you can find it easier. DE bigger than 0. Probability DE bigger than 0. So that's about, 1 in 5 right there. Now in general terms, if I went and looked over here, I would be able to reduce all of this to this general equation. And I'm going to let you do the algebra to show that that is true. So if I replaced, for example, over in this equation right here, if wherever I see this 2, I replace it with an A. Wherever I see this 3, I replace it with a B. Wherever I see this 5, I replace it with a big X naught. Wherever I see this 3, I replace it with a Y naught. And I'm going to really encourage you to show, I'm going to say, you do this. You show this It's good for your algebra muscles anyway. So that's the general equation that's actually in the textbook, equation 3.33. We're not quite done. We got one more slide to go, okay? All right. So now we got to put everything together. So again, remember what our objective is. What is the expected distance due to the barrier? It's the expected distance without the barrier plus the expected distance, the extra distance with the barrier. So now we're going to put this all together, and that's where that equation up here comes from. So we've got this and this and the expected distance here. I don't really like the way I did this, but just pay attention. I've kind of shorthanded this that way, but I prefer to write it this way. This is the longhand way. Remember, this is that second term when we actually broke it out in terms of the log total probability. So if we put this all together in terms of just the numbers here, my expected distance without the barrier would have been 1/3 x naught plus y naught, which we showed before was 2.67, which I showed before was just 8/3 miles. So that's from a previous slide. The expected distance, given that the distance is bigger than 0, we showed that that is, we just did that on a couple slides ago, we showed that this expected distance, just this term here, is 2/3 times the height of the barrier, which is A, and that was where we said that that was 4/3 miles. I forgot to put units on that. There we go. And then finally, we showed that the probability that we would have any extra distance ended up being a 0.213, and there's no units on that. So now when we put it together, we got the expected distance due to the barrier is the expected distance without the barrier, so that's what this guy is right here, rectilinear distance, plus now we've got this term. Well, you can put this all together. Where are we got here? This is 2 times BA, okay, right, so this right here is that 4/3 miles, so that is the 4/3 miles, and that would be the expected extra distance, given that the extra distance is bigger than 0, multiplied by, and that's what this is right here. This term is the probability that that extra distance is bigger than 0. And then you can combine those terms, and I promise you it works out to be this nasty looking equation. And for our specific example, we end up with that the expected distance due to the barrier is 2.951 miles, and compared to 2.67 if we didn't have the barrier there in the first place. So I know that took a long time for me to get through, and I'm sure it's hard to listen to my voice. It was hard for me, believe me. But I wanted to go through it fairly slowly. And again, be careful with this, because I think the book also does this. They just express the expected extra distance, but it is really this more complicated equation that we have to use. So I'm going to end here, and we'll move on to some other stuff in the next lecture.